and say good morning. Welcome back to a crash course in calibration model development. And so we're really getting into the meat now. We're going to talk about building a PLS regression model. Along the way, we'll talk about a few other uh, regression methods to get us to PLS. So regression is all about taking what's measured. In our case, that's usually spectra, and then having what it is that you really want, which in our case is concentration of glucose. So it's usually something like that or another property. And then relating one to the other. And let's see, which is how do we go from what we measure to what we really want? And that's really what regression modeling is all about. So regression analysis creates a mapping between two blocks of data. And that's in contrast to principal components analysis, which we just used to explore the correlation structure within a single block of data and find out what was going on with our samples, what variables contributed to the differences that we saw in them, etc. So PCA is a single block technique. Regression models are often used to obtain estimates or predictions for one block of data from the other. And of course, the reason why we do this is because it's easier to take spectra than it is to do the wet chemical method that we often need to get what's over here in the Y block. Let me turn my laser pointer on. That'll help. So it's generally easier to measure this than this. And so that's why if we build a model that relates the spectra to that, then we can just use this part here instead and infer this. So this is where I'll go with this morning. I'll talk just a little bit about inverse least squares models, which actually includes multiple linear regression, principal components regression. Once we hit PCR, we'll talk a bit about cross-validation, and then we'll introduce partial least squares, talk a bit about model quality measures, determining the number of factors, outlier detection, and model diagnostics. And then about that point, we'll actually do this, get into the software and use our glucose data set, and then make some conclusions. So inverse least squares models assume the form xb equals y plus e, and that is where your y is the property to be predicted, your x is your measured response, in our case our spectra, E is an error vector, and B is a vector of coefficients. So in the inverse least squares model says that we should be able to come up with some set of coefficients that if we apply that to our measured data, that should give us a prediction, an estimate for the property of interest. And that's the whole idea behind inverse least squares models. And the nice thing about inverse least squares models that include multiple linear regression, principal components regression, PLS, etc., they don't require that the concentration of all the analytes, including the interference, be known. Okay, so when you make the model, you only have to know what your analyte of interest, the one you're trying to predict, is doing. You need that for the calibration. But those other interference must vary in the calibration data set in order for the inverse least squares regression method to be robust against them. And we actually talked about this when we talked about the collecting data to make the calibration model out of. We already made this point, but I'm just making it again here. Uh, it does have this important implication for experimental design, and that is you have to make sure that these other things that might vary in the future when you're trying to apply the model also vary in the calibration data that you're deriving the model from. Otherwise, the model doesn't learn to ignore them. So again, an interferent is any substance whose presence interferes with an analytical procedure. So that's other analytes and other physical effects and instrumental effects, all of that stuff. Um, Interference that correlate with an analyte during calibration but don't in the future are to be avoided. Don't confound your design. And, they can correlate a little bit, but if they are really highly correlated with that, your property of interest, that's a problem. Don't confound your design, your experimental design. So how are we going to get this B from the inverse least squares models? Well, the most obvious way is to estimate it from multiple linear regression. And here I can write this really simply this way, and that is that our B is equal to some pseudo inverse of X times Y. And part of the reason I'm writing it this way now is we'll just show that when we do PCR and PLS, it's really the same thing. The only difference is in how you get this pseudo inverse. It's the same equation. So here, X plus is the pseudo inverse of X. And if you're using multiple linear regression, you just get that pseudo inverse of X from this, that X plus equals X transpose X inverse X transpose. And this is known as the Moore-Penrose pseudo inverse. And the main issue here is whether you're actually able to get this inverse here with your data. And that inverse is only going to exist. Let me see what my next slide says. Yeah, the problem with MLR, that inverse is only going to exist if the rank of X is equal to the number of variables in X. And that is the number of independent variations in the data. Well, the first problem is that the rank of X is always less than or equal to the minimum of the number of samples and the number of variables. That's my M and my NX here. So if I have fewer samples than variables, then this is not full rank. And this inverse won't exist. And of course, that happens all the time. In our glucose data set, I have 2,048 variables, channels in my Raman spectra. And I don't have anywhere near that many samples. So this isn't going to work to do multiple linear regression directly. That's a problem with spectra in general. It's also not going to work even if you have a small number of variables compared to the number of samples, if your columns of X are collinear. So that is if those are highly correlated or some are linear multiples of each other. So that makes it so you can't use multiple linear regression. You might get the instance too where you have an inverse that exists, but it's really unstable because X is nearly rank deficient. So that is that some variables in X are nearly linear combinations of others. We call this being ill-conditioned. In these cases, you can get small perturbations in the data that cause drastically different results, and that's generally undesirable. So one last comment though about multiple linear regression, you can do a procedure like stepwise to select a small set of variables to do multiple linear regression on, and that'll work and in a lot of instances pretty well, but you can't use your full data and do multiple linear regression most of the time when you're using spectra. So one solution to that is to use principal components regression instead. So principal components regression is one way to deal with this problem of too many variables and or ill conditioning. Uh, so that'll fix that. So what we actually do is the property of interest y is regressed on the principal component scores. And the pseudo inverse that we wind up with is this. So let's just think about that for a second again. We do PCA on a data set that reduces our number of variables down to however many scores that we kept in the model, how many PCs we kept in the model. And so now we just use those. And of course, those scores, that contains most of the information about how the samples in our data set relate to each other. So that information is really embedded in the scores. So now here our pseudo inverse is this, but let's look at it for a sec. T transpose T inverse T transpose, well, that's the part that we just before had all of X there instead of the scores. And then here's our loadings matrix right there. And what do loadings matrices do? Well, they take you back and forth between the world of original variables and the world of scores. So this translates essentially that result back into one that applies to all the variables. So that's the principal components regression. The trick now, of course, is that you have to determine K, the number of factors to retain in the formation of the model. So how many principal components do you use when you make the model? Okay, before we talk about that, just a bit about model quality measures. We like the root mean square error metrics for the most part, and there's three of those: the root mean square error of calibration, cross-validation, and prediction. The nice thing about those is that those quality measures are in units of the y variable. So if your y variable is in our case, milligrams per milliliter, these error measures are also in milligrams per milliliter. They're in the same units of that, and that makes them interpretable. Um, and here's how we get a root mean square error. Basically, what we do is we take the deviations between our property of interest and its estimated value from the model, take those differences, square them, add them up, take their mean, that's the 1 over m, how many of them there are, and take the square root of that. So it's the root of the mean squared error. And we have three ways to calculate that error: the error of calibration, cross-validation, and error prediction. That's in contrast to the correlation coefficient. Well, not a big fan of that. The correlation coefficient is unitless, and it also kind of implicitly considers the range of y, which is that for a given error of prediction, if your y values span a wider range, r goes up, it gets closer to 1. So the correlation coefficient is really sort of a relative measure between how far your points are off the regression line versus how spread out they are. Um, and it's unitless and not in the same units as the root mean square errors. Okay, so we want to determine how many factors to keep in the model. So we do cross-validation, and this will apply to both principal components regression and partial least squares. So we start by dividing our data set into J sample subsets. J is usually some small number, 5 to 10, somewhere in there is kind of typical. And then for each of the subsets, we build a regression model using samples in the remaining subsets. So that's kind of a funny way to say that. If I'm dividing this into 10, I build a regression model with 9 out of the 10 groups, and then those are my remaining subsets, and then apply it to the 10th one. And then I calculate a PRES, or predictive residual error sum of squares, for the left out samples. And that's just the difference, again, between our actual values and the ones predicted from the model. And look at that error. And then look for some knee or minimum in the cumulative PRES curve. And again, this is a root mean square error metric. It's the root mean square error of cross-validation. So we look at that. Graphically, cross-validation looks like this. Imagine that we just broke our data set into 3 subsets. So here I've got my X and my Y, my spectra and my concentrations, and I break this data set up into 3 parts. And in the first round, I'd calculate the model with the first two parts of the data and then use this third part of the spectra to predict its associated property values, and then repeat that. Now leave out the red part and make a model on the green and the blue and make a prediction from the red. And then in round 3, I'm leaving out the green part. Is that you, Neil?
Sorry.
Okay. Um, you don't disagree with that, do you?
Nope.
Okay. Okay, that's good. That's good. Um, so here's some typical cross-validation plots for PCR, and this one actually is on the glucose data. So here I've got my root mean square error cross-validation. Those are the blue circles, and the root mean square error of calibration, and that's my fit to the data where I don't leave any of it out. The root mean square error calibration is where I build my model on all the data and then I apply that model to all the data. So that's really a fit metric, whereas the root mean square error cross validation attempts to mimic how things actually work in prediction, where we build a model with part of the data and apply it to the rest of the data set. Okay, so a couple things to notice here. One is that the error of cross-validation curve here is a little higher than the error of calibration, and you always get that where, of course, you're fitting your data a little better than your ability to predict it. Okay, and here we have a couple of factors in our model that start down in error. By the time we add the third one, we go here to a fairly low error in this, and you can see we add more factors. We get a little something that seems to happen here about factor number 9. Um, and these things do begin to get a little further apart. One plot I've been using a lot lately is to plot the ratio of the cross-validation error to the calibration error versus the error of cross-validation. So really, if you imagine here taking the blue line and dividing it point by point by the red line, that's this right here. And then this is just the root mean square error cross-validation. So what I see here is as I add factors to the model, and I've just numbered them, um, things get better in root mean square error cross validation out here. And especially things get a bit better when I went from 3 to 4. I got a little lower cross validation error, and actually my overfit is better with this one. That's what this is measuring here. This vertical distance is uh, how overfit my model is, and that is how much tighter the model fits the data versus its ability to predict it. So generally you want models that aren't overfit and you want them to be predictive. So you really want your model to be over here in this corner somewhere. And in this case, 4 is pretty clearly our best point for that.
Hey Barry, we had a question in the RMS EC calculation. Do you subtract the number of LVs or also one for mean centering in your software?
No, we don't. And there's a reason why we don't. That turns out that actually what you're trying to do there is adjust for degrees of freedom. And you can do that actually in principal components regression, and it's pretty valid there. It's not really valid in PLS, and the problem is that PLS uses up more degrees of freedom than the number of factors in the model, and it uses them up real fast at the beginning, and then in the latter factors in the model, it's using them up slower. And so it's really uh, it, it can be estimated how many degrees it's effectively using, but it's a big pain and it's still kind of a research area. So rather than do it wrong, we don't do it. We just use the root mean square error of calibration. And of course, it doesn't matter much as long as you have more than 30 samples or so. If you've got a reasonable sized data set, that adjustment for degrees of freedom doesn't really make a lot of difference. Okay. Anything else?
No, we're good.
Okay. The problem with PCR is that you get some PCs that aren't relevant for prediction. They're only relevant for describing variation in X. And, an example of that is kind of this one here. This factor really didn't do much to improve prediction. It just described variation in the data. That's why it's here. Uh, and that leads to a local minima, an increase in press. That one actually wasn't a local minima, but I hope it illustrates the point a bit. And it's a result of the fact that we get our principal components without using any information about our property we're trying to predict, and in this case, our glucose concentration. So the PCs are just describing variation in the spectra. They don't actually know anything about what's going on in the property to be predicted because they're determined without using that information. So a solution is to find factors that use information from both y and x, and it's probably no surprise that that's partial least squares regression. And PLS is related to principal components regression and multiple linear regression. Um, and whereas PCR captures the maximum variation in x, and MLR achieves the maximum correlation between x and y, PLS tries to do both by maximizing the covariance between x and y. It requires the addition of these things called weights in order to maintain orthogonal scores. And the factors are calculated sequentially by projecting y through x. So I'm not going to go through PLS algorithms here. It winds up with this rather messy looking pseudo inverse. The sort of classic way to write it is this. You still have a part that has to do with the scores. And this part is a rotation matrix, if you will, and it's the weights that actually bring you back into uh, original variable space in PLS. You can lump this stuff together and just call it R if you want. It's important to note here that these loadings are not the same loadings as you get in PCA, and thus these scores are not the same scores that you get in PCA either. These scores are rotated to be more correlated with the property of interest than the ones that you get from doing principal components regression. So let's look at some typical cross-validation and our cross-validation calibration ratio plots for PLS. So here's one for the same data set that I did. This is for glucose data, that model. And I've put back over here the one for PCR on the right. And you notice a couple of things that are a little different. And that here, the PLS model, which is really more aggressive, if you will, because it's grabbing information from Y, starts down in error much more quickly than the PCR one. And it also begins to overfit faster. So you begin to get a big deviation here between the error of cross-validation and the error of calibration. So that generally doesn't happen much in PCR models because these factors that it's determining are independent of the Y values, if you will, because they're just determined from spectra only. So if you look at the ratio here from the PLS model, it looks like this. It goes out to 3, and then the overfitting really starts at with number 4. And you see that's right here. This deviation between these gets bigger and bigger, and this gets really big by the time you get out to 10. So these models out in here are way overfit. And just zooming in a bit on that, or I guess maybe I'm actually backing out. If I if I really backed out, you'd see that the out here by the time I hit 10, we're at I don't know, 10, 20, 100, somewhere out there. So the number of principal components or latent variables, the choice is not always simple, but remember, future prediction is the goal, not the fit to the data. So a couple rules of thumb, be conservative. Models are way more often overfit than underfit. That's everybody's temptation, is to produce overfit models. The best choice is often not the global minimum root mean square error cross validation. Look for a minimum and work backwards if the improvement isn't at least 2%. That's one rule of thumb. There's no theoretical basis for that. It just tends to work. If your error of calibration is less than your error of cross validation by more than, about 20% or so, it suggests overfit. That 20% number depends a bit on the size of your data set. If your data set has thousands of samples, then maybe that number ought to be 10%. If your data set only has 30, maybe you could go a little higher than 20%. Use this error of cross-validation over error of calibration ratio plot. I've found that to be really useful lately. And look at the variance captured in your both your X and Y and ask yourself if it's significant with respect to what you know about the errors in your data. So let's do a little regression example here on our glucose data. So we're going to develop a PLS model on the glucose concentration from this Raman spectra. And again, we've got 120 samples, we've got 2,048 wavelengths, and I'm actually not going to start by selecting the wavelengths of interest. Let's do it quickly without that. And here I'm going to stop my presentation. Oh, okay. I'll show you how to switch to PLS here if you didn't already know. Well, you'll see that when I start it. So I'm going to go down here. Uh, Before I do this, I'm going to show you something based on a question that we had yesterday. So yesterday we got asked about importing classes. And let me open up my Excel here. And uh, let me see. So here's my spreadsheet. Oh, darn it. Let's see. Don't save. That wasn't the one I wanted. Let me do this. Reset. There we go. Uh, so I created an Excel spreadsheet uh, for an experiment file reader where we had, as before, we had our file names and then we had concentration. I just took this concentration here and copied it over into something called class. And then when you import that, you can tell the import tool, it'll show you the first view of that, and you can specify that as a class. And now I not only have my concentrations in my Y, I'll also have these classes uh, assigned to my samples. And so I'm going to use my data from that. Okay, that I did. So let's start by um, loading our data up. Probably most of you cleared your uh, data yesterday. So here I've got my files. We saved yesterday this one called glucose data. And so that's usually where we start from. I've got my version of it that I put classes in. So I'm going to use that one. So in order to load that into the workspace browser, I just drag it and drop it and put it there. Okay. And so I've got glucose cons. I've got a model that I made here yesterday. and glucose spectra, and then glucose spectra with my class. So I'm going to start PLS up, and then I'm going to load these right here. So I'll start PLS by double clicking here on one of my favorite tools. And let me see. I keep winding up with my okay. Trying to get my there we go. Okay. Mike, the controls for the WebEx keep getting over the top of what I'm doing. So,
Can't control it
okay.
then.
No, you can't. I had to make it go away. So I'm going to say file, load data, load X and Y. And I'm going to use the one that I added this class information to. So glucose spectra class is my X data. And my Y data is glucose concentration, and I'll say load. And so here these are. I can see my X is 120 by 2048, and my Y is 120 by 1. I'm going to change my pre-processing to mean centering here, and basic methods mean center, just like that. And I'm going to leave Y as auto-scaled. That's fine. Cross-validation, let's just actually look at that. I'm going to click the check mark so I can show it to you. So here's the cross-validation window. There's a number of ways to split your data up. When you do cross-validation, we're going to use the one called Venetian blinds. And this just shows you the pattern of how your samples are going to be left out if you do Venetian blinds in your data. If I did contiguous blocks instead, it would make them in blocks like this. I really don't want to do that here. There's some other ways to do it, but I'm going to leave this at Venetian blinds. Maximum number of latent variables. I don't think we're going to use anywhere near 20, but it doesn't hurt anything. Number of splits in the data, we'll split it 10 ways here. So that means that, let's see, we have 120 samples. So each left out test set will have 12 samples in it. And that'll be fine. So I'll just say close. That's the way we're going to do this. So go ahead and get a model. Excuse me. And to get a model, I just click the big green button. And I'm presented with a table here that shows me the amount of variance captured in the X block or the spectra and the amount of variation captured in the Y block or the concentration. And this column shows me my error of cross-validation right here. A couple of things to note is that um, here in my first factor, I have 95% of the variation in X captures 97% of the variation in Y. So I can see right away that most of what's going on in this data set is that the glucose concentration is changing, the thing I'm trying to predict. I knew that already, uh, but that just confirms it. So let's look at our error of cross-validation. So here's what our errors of cross-validation look like. And this doesn't look very good just yet. For one thing, what happens here is by the time we're two factors into this, my model is way overfit already because I've got an error that's close to 1, but my fit is down here around 0.2. So that doesn't look too good yet, but you got to start somewhere. We do remember that we had some outliers in this data set. And so let's start by exploring it. So I'm going to just close that.
Hey Barry, what's the pre-processing here?
Just mean centering in X. So
And why did you not do it on Y? We have
it
a
it doesn't matter for Y. If you have a single Y variable, it makes no difference whether you mean center it or auto scale it. It does matter that it's centered, and auto scaling includes centering. But so I just left it as auto scaling. Doesn't make any difference. So if you want me to prove that, um, I'm going to change my Y to mean center and make the model again. And you'll notice all the numbers are exactly the same in the table as they were before. Doesn't make any difference. Okay.
Great.
Um, all right. So let's look at my scores plots, and that's the Erlenmeyer flask. So I just clicked on the Erlenmeyer flask. And actually this comes up with now my symbols, because I'm using the one that has classes in it, are class symbols here. And I can also have a legend in this, which I created for this. So here's my 5 through 40 milligram samples, and their symbols right there. So what do I see here? I'm going to turn the legend off. Um, well, the first thing I still have in the PLS model a Q residuals versus T squared, just like I do for principal components. And I see I have one sample that's very high in Q value, few that are lower but have higher T squared values. I see that my calibration curve here doesn't look too bad. It goes right through all the data. This is the, the cross-validated predictions versus the measured concentration. And of course, I want everything to wind up right here on the perfect prediction line. Um, I've got one sample here that doesn't. I suspect it's probably this one right here that I also see over here. This is the scores on the latent variable 2 versus 1. This plot right here is the studentized residual versus leverage. So leverage is actually related to the t squared value. It's a measure of the influence of a sample on the model. The studentized residual is how well that sample is predicted, and this is normalized to be essentially in units of standard deviation. So we expect that all of our samples should be 95% of them in the -2 to +2, 99% of them in the +3 to -3 range. So this one, for instance, I can see is being, way far out there. We already know what that sample is. That's the one that had the big baseline offset. So right away, I know I'm not going to use that one. And so I'm going to select that sample and get rid of it. So I'm going to choose this icon right here to select it, and going to go down here and do that. And sure enough, it got highlighted everywhere. And I'm going to go over here in my plot controls and say edit, exclude that selection. So that'll take that one out of there. And now, of course, I have to make my model again without it. And you see that a lot of our error over here was due to that. We were around 0.4 in error, and now we're all of a sudden down in the 0.1 something. So a lot of our prediction error was really associated with just that one sample. Again, if we look at our error across validation, looks like this. Okay, this begins to look a little better to me, because now these lines are much closer together. I might go with a fairly conservative model here to begin with, to explore a little more, maybe a 3-factor model. Really doesn't matter much at this phase because I'm still just looking around, but I'm going to set that to 3 for the moment.
We had a question about what LV to choose. I'm taking that you'll get to that in a little while about where you might want to make that decision.
Oh, yeah. I mean, one of the things I'm kind of showing here is it tends to be an iterative process where you find some things, and in this case, some samples you might want to get rid of. So let's look at this this model again now that we've gotten rid of our one major outlier. And I still see that I have a few samples that are interesting here. I've got some that actually have pretty high Q residuals, and it's interesting here because in my scores plot too, these are ones that are a little bit removed from where the rest of their groups are. Let me actually do that by doing this. I'm going to select some of these, and you can see where they are. I'm going to make one more selection here. So these samples, was I a sloppy clicker there? Maybe I was. Okay. Wow. Okay. One more time. I'm going to get it this time.
It doesn't want you to get there.
It doesn't want me to get that one. I'm pretty sure it's this one down here. Um, at any rate, you can see that the ones that I selected here are the ones that tend to be at the ends of these groups, a little bit split off. That one, that one, that one. And uh, so it may be that I want to actually get rid of some of those samples. So I'm going to actually start by doing that. I'm going to say exclude those. One of the things that I know here is I've got plenty of data, and for every single instance of concentration, I've got what 20 samples of it. So leaving a few out isn't going to bother me. I don't really believe they have essential information in them. So I'm going to exclude those. Remake the model. Okay, this is just generally how it goes. Um, Here my cross validation curve doesn't look a whole lot different. Back over here in scores, I still have a couple that this one is kind of an especially dangerous sample. It's predicted rather poorly, and it also has a lot of leverage. This one is maybe not as bad. It has a lot of leverage, but it's actually predicted not so bad. So I might consider getting rid of those. The other thing, recall that when we did PCA, that we did a little bit of variable selection here. So let's look at our loadings and see what's going on there. So this is the loadings in this PLS model. And here are my loadings in my first factor. And let's look at the loadings in the second one. See, that second factor isn't doing me any good because this part of it right here, uh, you can see, and that's part of what's just spreading my samples out this direction in my scores plot that doesn't have anything to do with the concentration of glucose in them. So I'm going to do a little bit of, of variable selection by hand here. And so knowing this and knowing this, just clicked on the wrong thing. Okay, knowing this and knowing this, I'm going to leave out this, leave out that, and leave out that. Again, like we did in PCA. So I'm going to change my editing here to my selection mode to be X range. And then I'm going to just select the parts that I want. So I'm going to choose this part here.
We had a question about whether information about the excluded data is retained. Um, and yes, when Barry is including or excluding, it's really kind of a soft delete where we're just telling the model to ignore these samples or these variables, but it's still in your data. And in fact, Barry could turn on the view excluded data, and you could see it in your plots.
Yeah, and I may do that later. And actually, when you uh, let me, I'll show you. Well, later I'm going to really show you about that, about the model detail also has all that information about what got excluded and what got kept. So here, this is the part that I really want. And so back in plot controls, I'm going to say edit include only selection. So include only the part that I selected. And so now I got to build my model of that right there. And of course, now that I've made that change, I got to rebuild my model one more time. And now we're at a point where we've got a pretty darn good three-factor model here. I've got 99.62% of the variance in X described. I hit 100 in Y in just three factors. So of course it's really not 100, but it's apparently greater than 99.99 and a half. So it shows as 100. So this is a pretty good model right here. No complaints about this one. Uh, okay. So this was a little bit of an abbreviated session on this, but I hope it gives you an idea of what the typical modeling process is like, where you go back and forth a little bit with deleting samples or changing what variables you're using, and to get yourself to a good model. So actually here, let's do what Scott suggested. I'm going to, uh, first off, let's just turn the classes off, okay? And let me see. I'm going to remake my scores plots here. So I turn the classes off. And I can actually, here in the plot controls, say view excluded data. And that will show me where everything falls. And you can see, in fact, that here, this was where the data that I excluded falls on this model. It really has really high Q residuals and high T-squareds. This is where it falls on the leverage plots. This is where it falls in the latent variable plots. Here, oh, this is CV predicted. I always do this. Yeah, it doesn't show up in a cross-validated prediction plots because it wasn't cross-validated on when it's left out. But we can just look at where the fit of it wound up, and here instead, and just put Y predicted right there. And that's where these points that I left out actually fall now. You can see the lighter colored ones right there. So you can see where they wind up in the model. And yeah, they're not nearly as well predicted as everything else, but they're not hugely off either. Okay, so let's go back to the PowerPoint.
I had a question saying, do we have to go through this iterative process after pre-processing methods are optimized?
Yeah, this is one of those things. It's like, well, should I do my sample selection first and then do pre-processing, or should I do pre-processing first and then sample selection? And it turns out that both are wrong. Which is that there's, in an ideal world, you'd optimize all of these things simultaneously. Uh, so you do need to go through the process, and there's a bit of back and forth in it. There's also, for instance, the possibility that when you change your pre-processing, some samples that were outliers aren't outliers anymore, depending on the pre-processing that you use. For instance, if I use a derivative pre-processing in this, that one sample with the offset, it doesn't look near as bad anymore. So it's a back and forth there, and I can't give you perfect way through it. That's why this normally takes a while to pick through the options.
And we had another question is it safe to keep some samples with high scores to potentially encompass fluke samples later with a model that uses them?
Yes, if you have some samples that are out on the extremes, if you think that your model is going to run into those in the future, then it would be a good thing to include them in the model. And actually, the real bummer is that the best thing to do would be to get more like them and then include those. And um, that's often very difficult because the model won't really model them very well if there's not very many of them compared to how much data you have. Uh, so yeah, that's always a hard one to know exactly how to solve. Like I say, it could be that you actually need more like that.
Barry, Jeff asked, how much should the warning of unusual hoteling t-squared values influence a user's selection of the appropriate number of latent variables?
Oh, not much. Mostly what we want you to do when we display that warning is to go look at them and see what you think. Basically, what that's saying is that you've got samples whose Q values or T squared values are far removed from the rest of the data. And so that is something that you should probably go look at. And then you got to decide. Okay. Just a couple of things that more before we finish this section. Model validation. Uh, all predictive models for both quantitative like this one and classification models should be validated with an independent test set. And I'm violating that rule here. That is a test set that is not used in the development of the model. It's best to collect this data on different days, maybe by different people or whatever, to make sure that the model is really capturing things that are reproducible, if you will, and works on that. Um, Validation should span the range of conditions expected during the model application. This might not be the same range as the calibration set. So maybe your calibration set has a pretty wide range of concentrations because by putting those in, it really helps the model establish its relationship between your concentrations and your spectra. But it might be, for instance, that when you use the model, you know that you're never going to get things out in that range. So you might want to just test it on a smaller range of your data. So that's possible, but models definitely should be validated with data that is independent of the calibration data. And that is, when I say independent, I mean has different errors in it, if you will. Um, okay, I'm not going to get too deep in the weeds on that. All right. So regression summary. We can divide models into classical least squares and the inverse least squares models. We didn't talk about classical least squares. And the inverse least squares models are all the ones that we've talked about today. Principal components regression and partial least squares work with ill-conditioned data by reducing it to a smaller number of factors. That has the advantage of signal averaging. We use cross-validation to determine number of factors, and I should say that that's not all we use. We look at also variance captured, and also how good is the model prediction compared to one, what we think the error in the reference values is, and two, how good does it have to be? So one of our rules of thumb here that I didn't mention is that we try to make models as simple, and that is as parsimonious with as few factors as possible to actually get the job done. So if they're fit for purpose, then don't keep adding factors to the model. And fit and prediction are two different things. That's why we get these differences between our error of calibration curves and our error of cross-validation curves, because it's pretty easy to really fit a data set closely. It's a much different thing to make it predict on new samples. And you should validate your models. So some resources, model development first. Uh, when you develop your model, you center and scale data as appropriate, you cross-validate, you check X block Q and T squared, Y block residuals for outliers, and then either remove or explain them or possibly get more. Look at your error cross-validation versus cross-valid calibration and see if it's overfit. Examine model scores and loadings for interesting trends. Sometimes that sends you back to the laboratory to get more data. And repeat is necessary. Usually you go through this loop a number of times. And this is one thing that, people don't realize is that it might take you a while to do this. If it's an important model, you might work on it for all day or maybe a couple of days. Of course, a lot of these models get put into processes where they're worth millions of dollars a year, so it's worth spending some time on them. When a model is applied, the data is centered and scaled by the model mean and variance. The measurements are multiplied by the regression vector to get scaled predictions, and that's scaled back up. Um, Prediction outliers can be found by calculating the Q and T squared values for new samples. And that's a really important point. We actually demonstrated that when I said show excluded data. We can calculate those Q and T squared values for samples that weren't used in the model development. And so that's all new samples too that are going to be applied to the model here. And so ones that have high Q and T squared values, we know not to trust the predictions on them because they're not similar to the data used to build the model on. And that's a very important aspect of these sorts of models is that they have those prediction outlier statistics. Of course, all of this stuff is packaged up. The model is an object that contains all the parameters, and so you don't actually have to worry about everything that's in it. So just some resources here. We have a couple of webinars on our webinar page. Everything you need to know about how to do partial least squares regression and everything you need to know about cross-validation. Those are both real good. And then, of course, our Eigenvector University courses, live and recorded. And EigenU will return to Seattle in May. So for that, how about before we do this section, we take a 5-minute break and I'll come back, say a few words about optimization, and then Bob will have some things to say about how to get models online.
We did have a couple of questions flow in here. Here's one that uh, we don't need to get completely derailed by, but maybe you have something to say. Does PLS predict better than PCR?
No, that's answered.
Great. Let's see here. I think there's a model deployment question here, and I'll let Bob look at that.
Yeah, I'll talk about that when we get to the model deployment section.
Then I had a question here. Do you have any examples where you're fitting more than just one component, or is it best to simply select each component individually and then model?
Okay, by component, I assume you mean analyte. So all right, you can put multiple analytes in the same PCA or PLS model. If it's only helpful to do that if they're pretty correlated with each other. If they're not, then it isn't. There's really very few instances where you can get better predictions by modeling two analytes in your Y block together as opposed to doing two separate models with them. Let me backtrack on that one that I answered no about PCR versus PLS. Um, it, it really PCR on average is as good as PLS. It's just a little harder to use because you often, well, really almost always have more factors in your PCR model because of the fact that they're determined without using Y information. And so PLS models tend to get to the optimum model in fewer factors, and then they also overfit a lot faster over that after that, but that's usually fairly obvious. So PLS models are generally just a little easier to make. They move more of the useful information up into the earlier factors of the model. That makes them easier to look at and investigate. And in terms of pure prediction error, they really there's no difference. Anytime I've actually ever tried to study that, I've come up with that they have the same predictive abilities, and um, I know other people who've done the same studies and come to the same results. So there you go.
Great. Coffee break.
Okay, yeah, sounds good. 5 minutes. Start my watch.